You're welcome to this physics class, and this time we are going to be handling theory question for the last physics exam. So this is just like a revision and also reviewing the past question. If you're ready, get your pen, get your writing material, let's get started. And I have the first question here. We said the force F acting on the wings of an aircraft moving through air of velocity v and density rho is given by the equation. So according to the force on the wings of an aircraft moving through the air, and the force is given as F is equal to K V power X, rho, which is density raised to power Y, and A raised to power Z, where K is the dimensionless constant and A is the surface area of the wing of the aircraft. Use dimension analysis to determine the value of X, Y, and Z. All right. Now, in dimension analysis, just like I've just told you in the previous video, dimension analysis is very great, and what I'm going to do is first, since this is velocity, I'm going to put dimension analysis for each of these quantities because they are derived quantities. These derived quantities, their dimension analysis will first be put, and that is your step one. Now, when we talk about force, force is mass times acceleration. What is the dimension analysis of mass? It's capital M. What the dimension analysis of acceleration is LT raised to power minus 2. That is the dimension analysis of force. The dimension analysis of V is given as LT raised to power minus 1. The dimension analysis of A is capital L squared. Now, all these 1, 2, 3, 4. Okay, density. Density is given as mass per meter volume. Therefore, the dimension analysis of density is going to be capital M is dimension analysis for mass, and then all over V is something as L raised to power 3, or sometimes I'll write it as capital M L raised to power minus 3. So this is dimension analysis of these three derived quantities. So the next thing I'm going to do is to sub all of them into the equation of the force. And that is given as F is M L T raised to power minus 2 is equal to V is going to be, okay, K. K is a dimensionless quantity, but I still have to put it here. V is given as this, and that is going to be T raised to power minus 1, and rho is going to be M raised to L raised to power minus 3, and A is going to be A raised to power what? 2. Oh, no, it's not A, it's L raised to power 2. Now remember, under V is raised to power X, so everything here on this V is going to be raised to power X. And everything here on this density is going to be raised to power Y. And everything here is going to be raised to power Z or Z. So let's keep going step by step. So after this, I'm going to have M raised to power 1, L raised to power 1 is equal to, T minus 2 raised to power minus 2 is going to be equal to K. I don't care with you. And this is power 1. According to the law of indices, the power will multiply power. This is going to be L raised to power X and T raised to power minus X. Then M is going to be M raised to power Y and L raised to power minus 3Y. Of course, this is multiplying this. That is power of 1. Y times 1 is this one. Then L raised to power 2Z. All right. Okay, so after that one, the next thing I'm going to do is to solve it according to law of indices, which I've been doing. This is application of indices, actually, like I told you. Now, in these indices, all the ones that have M, L, I have to bring them together. Look at them. So I'm going to say that all the ones that have M, they will also come together. All the ones that have T, they will also come together. So it's like a like term, not a like term actually, because we are not adding or subtracting, but then grouping, if that will be fine for you. So I'm grouping, I'm going to say, let me start from m. M raised to the power 1 is equal to, the first m is this, okay? So another m is here, raised to the power y. So what does that mean? According to the law of exponential equation or indices, when the two sides of an equation have the same base, their powers must be equated. This implies that y is equal to 1. Simple. I've gotten y. Yeah, I've gotten y. Let's go to the next. L, I'm bringing L. L raised to the power 1 is equal to, this is L, x, another L, minus 3y. You know why am I minusing? It's supposed to be plus, but plus minus is still going to give you minus. Now, what do I do? This is equal. This is implies that since the base are the same thing, their powers will equate each other. So this is going to be x minus 3y is equal to 1. All right? Remember, I already know what y is. So this is going to be x minus 3. Y is 3 times 1 is 6, 3 is equal to 1. So x is going to be equal to 4. Okay, so s is going to be 4. Do I have, oh my God, see. Oh, don't bother. So we have one more. I was wondering, so this is another L. So I'm saying L, 1, 2, 3. So this is going to be plus 2z. At least I'm free right now. So I'm having x minus 3y plus 2z is equal to 1. So I'm leaving this equation because it has two unknown. So I'll keep it that way. Then the next one is I'm going for t. T is raised to the power 2 is equal to t raised to the power minus x. Do I have another t? 1. These are the two t's. Okay, fine. So this implies that minus x is equal to minus 2. They cancel each other. Therefore, x is 2. Now, I have gotten x to be 2. So the next thing I'm going to have is going back to this equation to sub x, sub y, and find z. So in this one, x is 2 minus 3. 3 is what? Y is 1 there. Plus 2, z is equal to 1. So this is going to be 2 minus 3 plus 2z is equal to 1. 2 minus 3 is minus 1 plus 2z is equal to 1. This implies that 2z is equal to 2. Z is 1. All right, let me write it this way. After this, I found out that I have found my y. My y is equal to 1. My z is also equal to 1. And my x, where is x? My x is 2. So thank you very much. I have been able to find x, y, and z. So we are going to the next equation. Okay, the next equation says define strain energy. Define strain energy. Strain energy is simply the energy stored in a material, the energy stored in an elastic material because of the energy, because of the force applied on the material. So when you stretch the body, it expands. The energy stored in it due to the force stretched, or sometimes that potential energy is called strain energy. So in the B part, it said, write an expression for the energy stored E in the stretched wire of original length L, cross-sectional area A, extension E, and the Young modulus Y of the material of the wire. All right. Okay. Okay, the energy stored, E, that energy stored is given as half Fe. Average force times extension. Remember, force, energy is force times distance, and this is representing the distance. But then, because of energy, we have to consider the average force. So, but then F itself, force, is given as Ke. That is F. So I need to include the Young modulus, extension, and area. Therefore, I need to say that this Young modulus, which they wrote like Y there, is given as stress over strain. All right, stress itself, let me call stress Ss is equal to F all over area. So I've included F. F is there, of course. Yeah, okay, I've included F because F is there. And then strain, Sn, please accept this dimension, these parameters. And Sn is going to be given as original length, extension all over original length. So if this over this is equal to Young modulus, so I'm going to have that Young modulus is given as F over A divided by E over L, which is the same as F over A times L over E. Therefore, Young modulus is given as FL all over AE. But then I am looking for I will just remove this F and put this because I have included everything here. So this implies that F is going to be equal to this times this Young modulus A times E all over L. So this is F. I am going back to this equation to substitute it because they said I should write an expression that will include all these things in a wire. So I'm going to say that E is given as 1 over 2 bracket for F, and which is Young modulus A E over L bracket E, which is something as 1 all over 2 Young modulus A E square all over L. This is the expression we're expected to write. Let's go to number 3. Okay, number 3. A projectile fired at an angle theta to the horizontal with velocity u shows that at any time during the motion, the horizontal component of the velocity is independent of time. Independent of K, of time. All right. Show that at any time t during the motion, the horizontal component of the velocity is independent of time. All right. So let's assume this is a body projected with u at an angle theta. This is Vy, and this is Vx, and this is the origin. Now, as this body is moving, the body is moving up. At this maximum height, there is a place called maximum height. The vertical component of this speed will become 0 at maximum height. What does that mean? The body had a velocity 0. And what happened? At this point 0, the vertical component of this body is not 0 because we are using this formula Vy is equal to Uy plus Gt. You see this formula? This formula is what determines the velocity. Show that at any time during the motion, the horizontal component of velocity is independent of time. Okay. All right. So that is for. Okay. So this is the formula actually. And why am I putting Y? I am putting Y because it's all about the vertical component. But then this value is also initial vertical component. This is the final vertical component. But what we have to do is to resolve this vector. I told you that whenever a vector is inclined at an angle, there must be a resolution. A resolution must be taking place. If the body is moving on the vertical, you resolve this by vertical. If it is resolving on the horizontal, you move it to the horizontal. Therefore, since my question is interested in the horizontal component, I'm going to rewrite this one. That is modeling we are talking about. The model is, I am modeling the same equation for the vertical. I am also going to model it to the horizontal. So this one now is going to be ux. So what is this ux? Initial horizontal component. This is the final horizontal component. So what is this? And I'm going to do that because that ux is going to be equals to u cos theta. So in this case, this ux is going to be written in this format because I have resolved the horizontal component. At this point, 0 is called ux, which is the initial component. Why? Because at that point, time is 0. Now, we have Vx is equal to, instead of this u, I'm going to put u cos theta plus time is what? 0. If time is 0, then what are we going to have? Vx is going to be u cos theta, because this is at this point initial horizontal component. However, the question says here that at any time, so the one I have done is only at this time 0. What if at this point now the time has, let's say, has gone to, let's say, 2 seconds? What will happen? I'm going to put 2 seconds here, right? But then at this point the body is not moving in this direction. The body is considered to be horizontal component. At this point I'm going to be considering the Vx horizontal component at this point. But because gravitational force is not acting on the horizontal component, at that point I'm going to still have plus g is no longer going to be used. It's going to be 0 because it's not acting on the horizontal component, even though I put my time to be 2. So Vx is going to be u cos theta. Now you see something I have been able to show you. At any time, whether it is at this time, it's still going to be, yes, because here is 0. Of course, everything here was 0. So at this point, at the origin, it's still going to be u cos theta. At this point, t, I mean, when time has maybe gone 2 seconds, it's still going to be u cos theta. At the maximum height, I'm still going to have u cos theta. So what does it mean? It means that the horizontal component of any projectile is independent of the time. So the time does not change the value. Unlike the vertical component, the time does not affect the speed on the horizontal component for any projectile. That is the condition. That is so. I should show that the time is not independent. So time does not affect it here. Time does not affect it here. There is no place where time is affected, and that is the solution. A projectile is fired at an angle theta to the horizontal with the velocity. You show that at any time during the motion, the vertical component. So I will still go back to this formula. You are now interested in the vertical component. Because I am interested in the vertical component, I'm no longer going to use this. I will write this formula right now. I will change this x. It's modeling equation. I'm changing this to y. Why am I changing it to y? Because vertical has to do with Cartesian, up Cartesian. Horizontal deals with this Cartesian. Now, whenever a body is thrown vertically upward, acceleration due to gravity has been called into play. So as a result of that, g is very much alert. And then it says that it depends on what? Time. Good. So let's take first at this point. At this point, what do? I'm going to resolve this u into vertical component. Resolving to the vertical component, you are using sine. So I'm using uy is equal to u sine theta. So in this case, I'm going to say Vy is equal to u sine theta plus gt. Now, this is the formula for the vertical component of projectile. At any time means it is a job that people say Vy is a function of time. If I'm going into calculus, this is a function of time. Because the time here will be affecting it because g is considered. Now, let's go for the first one. When at this point now, initial velocity, initial vertical component of the velocity, time is 0. So I'm going to put time is equal to 0. So what will I have? I have Vy is equal to U sine theta. Time is 0, everything here is 0. So this is called what? Initial vertical component at this point. I call it point A. When I get to this point, point B, let's find what I have. And at that point, let's say that time is 2 seconds. So what happened? Let's go back to this demo. This is the main thing. I'll say that Vy is equal to U sine theta plus, at this guy, oh, if I say plus, oh, maybe I use minus. At the vertical component, let's use negative. So at this point right now, G is 10, and time is what? 2 seconds. So it can also be plus or minus. It doesn't. So at this point now, the value here will change because time has changed. When it gets to, let's say this point, when, let's say, time is 4 seconds, what will happen? Vy is going to be U sine theta, let's say plus 10, 4 seconds. So another value of V is going to be changing. Why is it changing? Because whenever the body is on the vertical component, then this equation is dependent on the gravitational field or gravitational force. So because gravitational force is involved, this formula is dependent on time because G is involved. That's what I would say there. Now, state 2 assumption on which projectile motion is based on. Projectile motion is based on, most of the times, you know, for a very standard physics question, there are things they should be saying, neglecting air resistance. So one thing they have to say is neglecting air resistance. State the assumption. One assumption is what? Neglecting air resistance. So air resistance must be neglected. So when you throw a body up, air resistance must be pulling it down. So, but we are deciding to neglect it. Number 2, it is an assumption that the body is moving under the gravitational influence. So there is a gravitational pull experienced by the body. So this is another assumption. Another assumption can be stated this way. You can say that it is also based on the fact that the body is moving under the strength of gravitational field or gravitational force. Mainly should be gravitational field. These are the 2 assumptions. State 3 differences between geostationary satellite and polar satellite. Okay? Okay, when we talk about geostationary satellite, we are talking about a kind of satellite that orbits with the speed of the Earth, that orbit in the direction of the Earth. So they follow the direction that the Earth is following. And most times they almost move at the same distance, at the same speed with the Earth. So somebody on the, another observer on the Earth will be watching, who is watching the satellite, will be seeing it moving in the same direction as the Earth or being stationary. You understand? Because when 2 people are running at the same pace and at the same level, somebody watching it may think that the 2 of them, another person watching it from outside may not even know that this guy is moving with the other person. So that is why they call it geostationary satellite. Now, what is the difference? One, it moves with the speed of the Earth, and that is one thing I would say. But then polar satellite does not move with the speed of the Earth. It moves with the speed and moves with the direction of the Earth, while polar satellite does not. Now, another one is this. Geostationary satellites provide a coverage on a particular aspect of the Earth. It provides a coverage on a specific aspect of the Earth. While polar satellite, because of this name polar, it orbits on the poles, north and south and north pole. That is how it orbits in that direction. As a result of that, it gives a wider coverage of the Earth. So this one gives a wider coverage of the Earth, while this one is giving a coverage on a particular aspect of the Earth. Number 2, this moves on the direction of the Earth, while this does not move on the direction of the Earth. And this moves with the speed of the Earth, and this does not move with the speed of the Earth. So with these tenses, you can combine 3 or more points to state your difference on geostationary satellites and polar satellites. Now, using kinetic theory, explain the term diffusion of fluid molecules. Diffusion of fluid molecules. Now, according to kinetic theory of matter, or according to kinetic theory, matter has molecules that are always in constant motion, colliding with the walls of the container. As a result of that, diffusion also involves the movement of these same molecules that are already in moving. These molecules are already in motion. So diffusion is the movement of the molecule of a substance from the region of higher concentration to the region of lower concentration. And the essence of this movement is to attain a uniform spread of these molecules. And they keep moving from one point to another in order to do what? To fill the whole environment and attain a uniform coverage in a given volume. So it involves the movement of these molecules from one region to another region in order to attain uniformity of the molecules. For example, when you put perfume, when you spray it, it moves from the source of where it is coming from and spread throughout the whole room. And that is one of the pictorial examples I want to give you about diffusion. Name one phenomenon that demonstrates that light behaves as a wave. I can say one may be diffraction or interference. It can be reflection or refraction. So one of them is there. And then name one phenomenon that demonstrates that light behaves as a particle. As a particle, it can be photoelectric effect. It can be Compton effect as well. Now, okay, this one says state one difference between an intrinsic and extrinsic semiconductor. When it comes to semiconductor, the one we call intrinsic is a pure semiconductor. A semiconductor like silicon or germanium, that has never been tampered with, is called intrinsic semiconductor. And at that point, the number of holes or the number of charges must be the same. From the electron, the positive charge and the negative charge is equal. It's just like you saying that atom is electrically neutral because the number of positive proton and is equal to the number of electron. So we have electrically neutral. It's the same thing when it comes to semiconductor. Intrinsic semiconductor is that kind of semiconductor where there is equal number of holes and electrons. Now when we talk about extrinsic semiconductor, we are talking about a conductor that has gone through an improvement. For you to want a semiconductor to act better, you need to improve it by doing what is called doping. That means an extrinsic semiconductor is a semiconductor that does not have equal number of holes and electrons. So one is greater, and that makes it extrinsic. So that is the best answer I can give. Okay, we have number 6B. It said draw a circuit diagram to illustrate full wave smoothing rectification. Rectification needs a diode. Diode is that component, electrical component that is used for rectification and which allows current to pass in one direction. So this is the diode, this is positive and this side is negative. So current flows from a higher potential, which is a more positive part, to the negative. That is a diode. Now, how do we use it for smoothing? What is smoothing? What we use for smoothing is a capacitor. Capacitor is mainly used for smoothing of a circuit. So I'm going to take that diagram as this. This is going to be my V in, that is the current in, source of energy, input value. So I'm going to connect them in parallel. So this is my diode. So my diode is moving in this direction. I'm connecting my diode this way. So then okay, then this is going to do my V out, that is the output of the voltage. But then this is nothing, this is just a kind of circuit, a circuit diagram, I mean, for electronics, for semiconductor. But then it's not going to be complete if I don't put what will help in the smoothing. And that smoothing is connecting parallel, a capacitor in parallel to this circuit. And this is the kind of circuit you need for that. And that is the essence of this capacitor. All right, what is optic fiber? What is fiber optic? Okay, fiber optic is a kind of technology which involves the transfer of data or signals using light over a long distance. And mostly it works on the principle of total internal reflection. And this optic fiber is a top-notch, is a new technology in terms of transferring signals and data. It's very fast because with light is better. All right, the next question says, state 2 reasons why optical fiber are preferred to copper cables in the telecommunication industry. In the olden days, kind of signals and data transfer was copper, but the use of optic fiber has made it better. One, in transferring a very large data. One of the reasons why we prefer it, one, large data transference. It allows a large data to be transferred. Number two, I will say, is speed. Because we are using light to do the transfer, the speed of light is far better than that when copper was used. Another one is long distances. It can transfer data over a very long distance without loss of signals. These are 3 major reasons why I think optic fiber is better or preferred over copper cables. State the reason why simple harmonic motion is periodic. What is simple? For you to answer this question, you first need to know what is simple harmonic motion. Simple harmonic motion is the to and fro movement or vibratory movement or oscillatory movement of an object in a straight line such that its displacement is directly proportional to the acceleration and it is always directed towards the center. So one reason is that one, the displacement must be directly proportional to the acceleration, or the acceleration must be directly proportional to the displacement. And that's number one reason. And another one is that the acceleration must be directed towards the center. There must be a center of equilibrium and it must be directed towards the center. So a few reasons. From the definition, you can pick out the reasons. State 2 factors that affect the period of oscillation. Factors that affect the period of oscillation from this formula, 2 pi L over G. This is for simple harmonic motion, of course, simple pendulum, because the other one can also be this. So there are two. This is for a spring, while this is for simple pendulum. And for that reason, I don't need this. So period T is directly proportional to square root of the length. And T is also inversely proportional to the strength of the magnetic field. Therefore, the period is directly proportional to the length of the pendulum, and the period is inversely proportional, or simply period depends, or the period affects the gravitational field, or the gravitational field affects the period. So the main thing is that the length is there and the gravitational field. A graph of the total mechanical energy E, this displacement Y, for the motion of a simple pendulum from one extreme position to another. Okay, these are good questions. If I have a graph, this is E, energy, this is equilibrium position. There are two, and this has to do with position. Okay, position in this case, I'm using Y, not X. So there must be positive, there must be negative because of the restoring force. So at this point, kinetic energy, V is 0 at the extreme, and it's maximum here. Okay, so I will also have this. I'm going to start with this. I hope this is not a terrible diagram. Then this is the first. We'll find out this is called potential energy, because potential energy is maximum at this point. So then the next one, so at this point now, we are saying E is equal to kinetic energy plus potential energy. So the total mechanical energy is E. Now, at this point, where this graph is representing potential energy, why this one is representing kinetic energy. So this is just the graph, and this is the position for the amplitude, positive for here, and here is negative. So at this point, V is 0, because it has come back to this, because for this to be kinetic energy, coming back to this line, at this point, K is 0. Potential energy is 0 at this point. But then, at this same point, potential, so I hope I'm not wrong, kinetic energy is 0 here, and potential energy is maximum here. I am correct, this is correct. Maximum kinetic energy, because at this point, this place has gone maximum. So this E is the total kinetic energy, total mechanical energy. The diagram below illustrates an oscillatory pendulum. Okay, calculate the work done in raising the pendulum to a point B if the mass of the bulb is 50 grams. Okay, the work done is going to be energy, of course, and through this height from to a point B, okay, from here to here, and that must be potential energy. That is the work done. Okay, from this point A, raise it to point B. It must be, the work done must be this, which is the energy. And that must be, the height is 10 mgh. M is what is the mass of the body is 50. Okay, 50 grams, which is going to be 50 over 1,000. Yes, converting it to kg, multiply by 10. G is 10 over 1 times. Height is 10. So 0 cancel 0, 0 take this, and we have 5 joules. So the work done is 5 joules. Okay. Now a spring of spring constant K, natural length L, has a scale pan of 0.04 kg hanging on its lower end, while the upper end firmly fixed to a support. When an object of mass 0.20 kg is placed on the scale pan, the length of the spring becomes 0.055 meter, and when the object is replaced with another object of mass 0.28 kilogram, the length of the spring becomes 0.065 meter. Calculate the value of K and L, and G is 10 meters per second square. All right, so in that case, I have that the spring has a length. I do not know the length. I'll call it L. Then another one with a scale pan with a scapan of mass 0.04. Okay, now, what I'm going to first look up is, I'm going to be adding, because the mass of the scapan plus the mass you are loading is going to be my total force. Lower end fixed support, when the object of mass, okay? So I'm going to say this one is going to be 0.2 plus 0.04. Yeah. 0.04, correct? Then I'm going to use this. According to Hooke's law, F is equal to KE. And the F can be weight, because this can be weight. And that is going to be mg is equal to KE. Yes, I will use this one. But remember, the length here has increased. The extension has increased because it's no longer original length. Then by how much did it increase? And the object of this, okay, let me just get the values. Lower end, why the upper fixed point to support? When an object of mass is placed on the scapan, the length becomes, okay, the length becomes 0.055. So I'm going to say that extension is going to be 0.055 minus the original length. This is my extension. Knowing this, I'm applying it here. Then, but the total mass is going to be 0.24 kg. Is going to be the total mass. All right? Now, I'm going to apply this formula, which is this. So what am I going to do? I'm going to say mass is 0.24 times G is 10 is equal to K. I don't know K. Multiplied by extension is going to be 0.055 minus L. So this is going to be 2.4 is equal to, okay, K bracket 0.055 minus L. So let me keep this equation first, because something else happened. So after the first one, we now said, and when object is placed with another is replaced, that means if I remove this object, the spring will go back to the original. So when I put another one, a new extension is formed. So that is 0.28. So 0.28 plus 0.04 is going to be 2. Okay, so this is going to be, this into this is 12, right, 213. 0.32. This is going to be the total force. I'm still using this formula. And that is going to be 0.332 times 10 for mass and G is equal to K. K is still going to be the same because it's still the same spring that was used in the same second experiment. And what is going to be the new extension, the new length? Okay, and the length becomes 0.065. So it's 0.065 minus the same length. So I'm having this, the first equation, and this is the second equation. So if you check very well, what is common between this and this is K. Therefore, I'm going to say K is equal to 2.4 all over 0.055 minus L is equal to, another K is going to be, this is going to be 3.2 all over. I'm making K the subject formula in the first equation, and I'm making K the subject of formula in the second equation. Then when they are the same K, I equate them. That's just what I'm doing. So I have 0.065 minus L in the second equation. So having this, let's solve for L and then later find for K. So let me keep that K is equal to 2.4 all over 0.055 minus L. Let me keep this. So I'm going to clear the fraction. 2.4 multiplied by 0.6, 2.4 times 0.065. So this multiplied by this, I'm going to have 0.156 minus 2.4L. You know what? This times this times this, I'm having this. And this is equal to, so 3.2 times 0.055. 3.2 times 0.055. 0.176. 0.176 minus 3.2L. All right, so So I'm going to, deal with the mathematics. So I'm carrying this to this side. So I'm going to have 3.2L minus 2.4L is equal to 0.176 minus 0.156. So I'm having 0.176 minus 0.156. I'll have 0.02. This is going to be 0.02. And this is going to be 32 minus 24. 3.2 minus 0.8 L. So L is going to be 0. Divide by 0.8. L is going to be 0.025. Is it meter? Is meters. So this is the value of the length of the spring. And the size should also calculate the value of K. I'm putting it here. So K is equal to 2.4 all over 0.055 minus 0.025. Okay, I'll have 2.4 divided by 0.03. So K becomes, I think, 2.4 divided by 0.03. 80, what is the unit of this constant K? KE, okay, that is Newton per meter. Newton per meter. So this is the value of the, all right, so let's go to the next question. Define each of the following terms used by the simple machine. Pivot. Pivot is just the point of turning. The point, every simple, like I'm turning right now, the point through which I'm turning, the point about which I am turning is called the pivot, the fulcrum. The pivot or the fulcrum, the turning point, the person who is allowed to turn, not the person. The point through which anything turns is called the pivot. So define the following used by simple machine. Load. Load is the weight which effort is needed to overcome. Or weight, load is that weight or the mass which machine is used to overcome. That is the load. Nothing special. Sometimes it can be expressed in gram or it can be expressed in weight, depending on your question. Efficiency. Efficiency is the work output over work input times 100 over 1. And most times, machine can never be 100% efficiency or 100% efficient because friction is involved and some energy is lost in order to overcome the friction. So that is efficiency. Okay, we have number 9. Okay, that's number 9B. He said a truck of mass 1.2 times 10 raised to 3 kilogram is pulled from rest by a constant horizontal force of 25.2 Newton on a leveled road if the maximum speed attainable in the process is 60 kilometers per hour. Calculate the work done by the force. All right, the first thing I have to start doing is to convert this kilometer per hour to meters per second because that can never happen. We cannot use, so I'm going to say 60 times 1000 divided by 3600. I am converting from kilometer hour. I'm converting from kilometer per hour to meters per second. So I'll just multiply the value by 1000 divided by 3600. So when I have that, I have 60 divided by 36. 600 divided by 36. 16.7, 16.67. So this is 60 times 10 because these two zeros cancel these two zeros, remaining this one and this one. So this 60 times 10 is 600 divided by 36 is 16.67 meters per second. So this is the velocity. And I'll give him mass as 1.2 times 10 raised to the power kilogram raised to the power 3 kg is pulled from rest. Rest means U is 0. initial velocity is 0, and a force. All right, there are two formulas for work. Work can be force times distance. Work can also be change in kinetic energy. I think the right thing to use here is change in kinetic energy. So work is equal to change in kinetic energy. That means kinetic energy is half mv squared minus half mu squared. Yes, because this is final kinetic energy and this is initial kinetic energy. When you subtract all of them, you have work. And why do I need this? I have the parameters to do that. So this is going to be 1 over 2 times 1,000, 1.200, which is 1.2 times 10 raised to the power 3. V is final, which is 16.67 all squared minus, I think that is 0 squared. All right, so at this point, I'm going to just simplify this. I don't want stress. That 16.67 squared times, and this is going to be 1200. 1200 is equal to, divide by 2, no, times the 2, divide by 2. Have 16, yeah, I think that's correct. So I'm having the work done is going to be 16.16633.34 joules. This is the work. So this is the work done. All right, the next question says, the next question is saying, if the maximum speed, okay, all right, that's not the next question. Now the next question says, a truck of mass 1.2 times 10 raised to the power 3 kg is pulled from rest by a constant horizontal force of 25.2 Newton on a horizontal level road. If the maximum speed attainable in the process is 60 kilometers per hour, calculate the distance traveled by the truck in reaching the maximum speed. Okay, force times distance, I have work, and I have given force. Let me use force formula. I think in that case, I'm still using that value. I'm going to use, acceleration is going to be force over A, because F is equal to ma. So force is, what is force? 25.2. Mass is 1200. So what is acceleration? 25.2 divided by 1200. Okay, acceleration is 0.021 meters per second square. Then at that point we have that, okay, I'm going to use this. So I'm looking for the distance traveled, which is x. I have final velocity, which is this value. So I have 16.67 all squared is equal to, this is 0. This is 2 times, acceleration is 0.021 times x. So I'm dividing this 16.67 squared, then divide by, so I have 277.889 is equal to, which is going to be 0.042 s. So I'll say s is going to be 277.889 divided by 0.042. 277.889 divided by 0.042. So S is given as 6616.4 meters. All right, that is the distance according to this question. The next question is differentiate. State two differences between absolute zero temperature and the ice point. When we talk about absolute zero temperature, we are talking about zero measured by a Kelvin scale. Kelvin scale is used to measure temperature as well as Celsius scale or Fahrenheit scale. But whenever you want to find absolute zero, it is that zero measured by Kelvin temperature. Why ice point is the point of is the temperature which is zero for water. Water at the freezing point has a temperature called ice point. So when you talk about this point, it's temperature. So this is zero temperature according to Kelvin scale, and this is zero temperature according to Celsius scale. This is zero temperature according to Celsius scale. This is zero temperature according to Kelvin scale. The next one is at this temperature called zero temperature, heat energy is almost zero because the value is too low that organisms and every other thing may not survive. It is the lowest possible temperature. While at this particular temperature, the difference is at this one, life can still exist at 0 degrees Celsius because 0 degrees Celsius is nothing. It's nothing compared to zero temperature. At zero temperature, practically nothing can exist at that point. Everything is squeezed. Like, can you imagine inside your fridge is 0 degrees Celsius, right? Imagine when you have minus 10 degrees Celsius. Minus 10 degrees Celsius is not even close to zero, absolute zero. So absolute zero is the temperature at which life is practically impossible to exist. We have a question here which is an uncalibrated liquid in glass thermometer was used in determining a Celsius temperature. The readings are tabulated below. Temperature 0 Celsius, temperature in degrees Celsius, minus 60 and 100, and the length of the column in cm is from L to 2 to 150. Let's find out how we are going to solve this. I'm going to just use a very simple approach. So I'm going to draw this. This is going to be my 0 and 100. But then after 0, okay, let me call this place 0, and this is going to be minus 6. This is for my Celsius scale. Then I have the other length of the column, which I'm going to write according to the way it was placed here. This is L for 6, and this is 2 for the 0, and this is 100. Okay, that is 15. So I'm going to take it this way. Look at what I'll do. 100 minus 6. So this is going to be 100 plus 6 all over 0 minus 6, which is going to be 6. Then this is going to be equal to 15 minus L all over 2 minus L. So I'll add up. This is 106 all over 6 is equal to 15 minus L all over 2 minus L. So I'm going to, do the solution. 106 divided by 6 is going to be 17.67. 17.67 is going to be equal to 15 minus L all over 2 minus L. So let me finish it up here. So this is going to be multiplied by 2. I'll say this multiplied by 2, which is 35.33. 35.33 minus this times L, which is 17.67 L, is equal to 15 minus L. So I will take L to this side and bring 15 here. This is minus 15. So I have 35.33 minus 15, which is equal to 17.67 L minus L. Now this minus 15 is going to be 20.33. 20.33 is equal to, this is going to be 16.67, 16.67 L. So L is equal to 20.33 divided by 16.67. So this is 22 meters, or in cm, that will be in cm. All right, so that is the answer for that question. Why are parabolic mirrors suitable for use in headlamp of vehicles? Parabolic mirrors can cover a wider range, that's number one, and it has high focus power because of its ability to direct the beams. For its ability to direct the beams and its power of focus, and then coverage of wider range, because parabolic mirror is a special case of concave mirror, because it's also a spherical mirror, but then it's supposed to be concave, but it's a special case of concave mirror, which gives a very powerful focus. So that's what I would say on that. So draw a ray diagram to illustrate the answer in number 10. Okay, at this point, just like a concave mirror is this, I'm shading the other part, and I'm using the inner part. This is the same thing a parabolic mirror is, and there must be a line which passes through the pole, and that line is called principal axis. Then if I put a source of light here, then which will direct the light here, then there will be a reflection. Okay, another one hit here and reflect this way. It will reflect. So this is the focus, which is also a source of the light. So this is the diagram which explains how powerful it is. This is called parabolic mirror. And that is the diagram they want us to draw. State 2 applications of echo. In application of echo 1 to determine the depth of the sea in submarine for oil exploration. That's the 2 I have for you. An observer at a point P on, okay, this is a calculation question. An observer standing at a point P on the same horizontal ground as the foot H of a tower shouts, and 1.2 seconds later he hears the same echo. He hears the echo. He then moved to another point Q 40 meters from P and shouts again, but the echo was heard 1.45 seconds. Calculate the distance between H and P and then the speed of sound in air. All right, according to speed of sound in air for echo to occur is 2x all over t. Now let's assume that this is the tower and this is the point P. And that point P, how many distance? What is the distance? Observer point on the same horizontal ground. He hears echo. He moved to, okay. Okay, now this is x. I don't know the distance. So what I'm going to say here, I'm going to say, I'll call it the first T1. I'll say V is equal to 2x all over. The first T is 1.2. So this is 1.2. I'm keeping this as equation 1. Now, he hears the echo. He then moved. So the next one, he then moved to another point, 40 meters from P. Then another time, he moved to another point here. Let me call this Q. Of course, it should be Q. 40 meters, from P. He shouts again, but the echo was heard 1.45 later. So from this point now, V is still going to be 2 instead of x, because from here to here, it's going to be 40 plus x all over 1.45. This is equation 2. So what happened? Calculate the distance between P and Q and H. Okay, this is P and this is H. I'm looking for x. First, I'm going to equate them. Why will I equate them? Because the same speed of sound in air here is same speed of sound in air here. So I'm going to say 2x all over 1.2 is equal to 80 plus 2x all over 1.45. So I'm clearing the fraction. This is going to be this is 2.9. This times this is 2.9. And this is going to be equal to 96 plus this is 2.4x. All right, this is supposed to be 2.9x. So so this minus this, because coming this is going to be 0.5x is equal to 96, which is going to be 96 times 2. 192 meters. So x is 192 meters. X is 192 meters. So the next question said speed of sound in air. I'll just put it here. So I'm going to have that v is going to be 2 times 192 divided by 1.2. So I'll just put this way, 2 times 196 divided by 1.2. So I have v is going to be 326.7 meters per second. So that is the speed of sound in air. Next question. Define the term absolute refraction, absolute refractive index of a medium. Absolute refractive index of a medium. Absolute refractive index of a medium is defined as the ratio of the velocity of light in the vacuum to the velocity of the media. For example, refractive index is going to be velocity of the sound in the vacuum all over the velocity of sound in the given medium. That's the ratio for the two. Then we have this question. A piece of coin falls accidentally into a tank containing two immiscible liquids, A and B, illustrated. When we talk about immiscible liquid, we are talking about liquid that can never mix. For example, oil and water, as shown in this diagram. So from this is the medium for the first liquid, which has a real depth of 8 cm. And then this is another liquid of length, which is real depth of 40 cm. And this coin, you know what happens to this is all about real and apparent depth. These coins will never appear to be here. So what are we looking for? Calculate the displacement of the coin when viewed vertically from above. Refractive index of A is 1.3. Okay, this is going to be simply find the displacement for A and displacement for B and add them. And how do you do that? The displacement for A is going to be, it should be the relative density. No, it's going to be the real depth multiplied by 1 minus 1 all over the refractive index. The real depth. So this formula is the formula used for finding the displacement. The displacement where, I'm sure you know that when a body is inside a refractive liquid, or let's say medium, when you are looking at it through the medium, it will not be the same. So we have real depth and apparent depth. The derivative for finding the displacement is this formula. So let's go for A. The displacement for A is going to be, the real depth of A is 40. 1 minus 1 all over the refractive index of A is 1.3. So this is going to be 40 minus 40 over 1.3. So let's go. So let's say 40 divided by 1.3. 30 point this. Okay, so this is going to be 40 minus 30.77. Don't mind me. This is going to be 10.77. 10.77 in meters or cm. Oh, sorry, 9.23. This is going to be 9.23 cm. All right, the displacement for the second liquid is going to be, the read depth is 8. 1 minus 1 all over the refractive index. So this is going to be 8 minus 8 all over 1.4. So 8 divided by 1.4 is 5.7. So 8 minus 5.71 is equal to is going to be 2.29. Now the total of them is going to be added. So I'm going to say 2.29 plus 9.23 11. So the answer is 11.52 cm is going to be the total. The total. That is the length you are going to see it when you are viewing it from above. All right. Define electric potential at a point in an electric field. Electric potential at a point in an electric field is the work done in moving a unit mass from infinity to that point against the electrical field. In fact, simply put, it is the work done in moving a unit positive charge from that point, from infinity to that point, and that will be fine. An uncharged body A was charged electrostatically by a test charge B using the method of induction and the method of contact. State two differences between the two methods. One, in the method of, let's talk about the first one, which is induction. And induction is simply a redirection, or let's say redistribution of the charge. For example, you have, this is a charged body, and this is the uncharged body. By bringing it close to it, not touching it, what happened? The charge from here is distributed to this charge. However, if it is like this, if the body, uncharged body is like this book, and this body is positively charged, positive and positive will no longer work now, because at this point, positive here, there will be negative here, while the positive will run away to this side. So that one is what is called induction. And as a result of that, what is the, because that they said, there's another question, is said the differences between the two methods. Okay. The first method of induction, the difference is this. The charged body we induce a different charge to the body. For example, if this is positively charged, after induction, this body will be negatively charged. But for the other one, which is called by contact, contact of course is this and this touching together, and contact occurs. And the difference is this. For a contact, the charged, if it is positively charged, it will give a positive charge to the uncharged body. So that is the answer for this. An important precaution during electricity experiment is to open the circuit when no reading are being taken. Give 2 reasons for the stated precaution. Well, one is to preserve the energy of the cell, because when the cell is always connected and you are taking your reading, even after taking your reading, then the energy will be taken away. Another one is that number 2 is this. Provided there is potential difference, I mean the charges are moving, whether the ammeter or the voltmeter will be overheating, and because of that there will be inaccuracy. There may be likely have an inaccuracy in reading. So what I'm saying in the second reason is that it is always good to open your cell. If you don't open it, as the current is flowing, your instrument may be overheat, and that overheating will lead to giving wrong answers to your reading. So accuracy, number one, and number two is loss of energy by the cell. All right, and in figure 11.0 is a circuit diagram in which a coil of inductance L and a resistor of resistance R are connected to a variable alternating source of frequency, F. Now, this is the resistor and this is the inductor. This is 240 volts and this is the frequency. In the table shows a square of the impedance Z squared correspond to each of the value F. All right. Write down the equation for Z in terms of F, R, and L. All right. In RL circuit, in LR or RL circuit, we have that total voltage write down the equation for Z in the terms of F. All right, so I have VL. This VL is the voltage across the inductor. It is given as 2 pi FL. Yeah. And according to this, there is a resultant voltage. The resultant voltage is called V. It's going to be because of the voltage across the resistor plus the voltage across the inductor, all in this format, like the resultant voltage. So for that reason, I will say that, and this V is something as IZ. This V is IZ all squared is equal to VR is I multiplied by R all squared, of course, plus VL is 2 pi FL all squared. So this is going to be I squared Z squared is equal to I squared R squared plus 4 pi square F square L square. Write equation in terms of F, R, L, of course. So what I'm going to do, I'm factoring. Okay, I am taking this to this side. I want L to be alone. So what I'm going to do is Z squared is going to be I okay, so it's going to be I square R square plus 4 pi square F square L square all over I square. That is how I will put it because I couldn't factor out I, so they can't cancel. So this is the way. So as I said, I should write down the equation in terms of F, R, and L. So I have F square, I have R square, I have L square. So that is correct. All right, let's go to this number 12 right now. State the function of each of the following parts of a modern X-ray. I think I'm not asked to draw actually. The modern X-ray, the heater. Heater is like the filament which provides, if you are here, maybe you have a picture of a modern X-ray, you understand. So there is a point called heater, and that heater is the point of filament. What is filament? Filament is just a metal which when heated can give out electrons. So they act like a cathode for, maybe through the help of thermionic emission, they give out electrons. That is the heater. The next one is high tension source. This high tension source is like a very high voltage connected across the positive and negative of the X-ray. Because without a very high voltage, then we may not be able to have an X-ray tube. So this high tension is that which provides a high potential difference between the ends. Cooling fins. This is the place which provides cooling to the heated part of the X-ray. And they do that by extracting the heat and taking it to the external environment in order to keep the temperature of the X-ray normal. Gas envelope is highly evacuated. A gas in the tube must be evacuated. Why? Because when the gases are there, it will not really allow the electrons to have a free access from the cathode or from where it is heated to the target where it is needed. Because without that, then the X-ray will not be very good, because the electrons has to hit the target, which is called the anode. So you need to evacuate it so that there will be no much air, to avoid so much of ionization with the air or reaction with the air. As a result of that, the air prevents its movement. You know that even a human being, when the air is blowing, running is very hard for you. So when you remove air, you see how human being would have accelerated. And that is why most times physics will tell you neglecting air resistance. So what they did in that air evacuated tube is to use vacuum tube to remove the air in order to have free access. So what the gas there is for removing the air. We state one reason for each of the following design features of a modern X-ray tube. A target is a metal of high melting point. Yes, the target is where the electrons hit. You know, whenever something is running, whenever something is moving at a high speed, they will have a very high temperature, because temperature is the average kinetic energy of the molecules. Now, electrons, when they hit the target, their temperature is very high. So the target itself must be at a very high melting point. The temperature must be very high in its melting point in order not to destroy or melt that particular element. So that is it. Cooling fins are located outside the environment. Yes, the heat must be in the outside environment, not the inside, because the temperature of the inside, we must be maintaining it at a certain temperature. So the cooling fin must be given an outside so that the heat extracted can be taken to the outside. All right, we have in a nuclear fission reaction, a nuclide 235 uranium 235-92 is bombarded with a neutron to produce nitrate, krypton, and baryon 14156. With additional neutrons, the energy involved in the process is mass of the uranium, mass of the krypton, mass of the baryon, mass of the neutron, and 1 U. That U means unified atomic mass. That is why I didn't mention them here. Unified atomic mass, UMA, unified atomic mass. And then C, which is the speed of light, is write down the balance equation, nuclear equation for the process. All right. All right, the equation should be U 235 96 92 plus uranium, neutron. This is neutron, must be equal to. The first one there is nitrate 36 plus they mentioned additional, okay, plus baryon 14156 Ba plus, it depends on the number of the neutron I'm going to put, because they say additional, of course, and this is fission. Maybe in power plant, in that process, other ones will be released, or chain reaction. So I'm going to say plus Q, because excessive heat must be released. So what should I put here to balance 2, 3, 5 plus 1 is 6. So this is nitrate and this, okay, so I'm going to put 2. So this is going to be plus 210 nu N, because if you add it, 93 plus 141 plus 2, because 2 times 1 is going to be 2. So the total atomic mass must be balanced for the two reactions. That was why I told you in physics, you must always have a law of conservation of energy. It is applied here. Okay, so that is the equation we are asked to write. In the nuclear fission reaction, okay, we have read this before. State with reason whether Q is absorbed or released in the process. All right, the reason for Q to be absorbed or released, the mass of this side must be greater than the mass of this side before we consider the absorption or its absorption or release of the energy, because this is the energy released as a result of the mass defect is what is going to lead to the release of this energy. Mass defect means imbalance between the masses of the parent atom and the daughter element. All right, let's go to the next one, which is calculate the value of Q. Okay, from here we answer that question. Calculate the value of Q. Now, this was given, the value of this was given, the value of this. So let's find the total mass of the element in this left-hand side of the equation. So that is 235.044. 235.044 plus the mass of this, so it must be U plus neutron. Neutron is mass of one neutron, 1.009. 1.009 U. Okay, so we add the two of them to find the total mass on the left-hand side. 235.044 plus 1.009. So this is going to be 236.053 U. So this is the total mass on this side. Let's find the total mass on this side. All right, so for the krypton, it was given to me, the value was given to me, 91.89. Okay, so I'm going to say 91.8898 plus the other one, baryon. The baryon is going to be 140.914. Then, so let's add that. That's going to be 91.898 plus 140.914 plus 2 times the value of this. 2 times the value of this. So we are going to have 2 bracket 1.009 U. Remember, all of them must be in U, unified atomic mass. So let's add this all together. So I'm going to have 91.898 plus 140.914. So when I added everything here, I'm going to have 234.83 U. Now look at this. There is another mass there. So the two of them subtracting each other is going to give me the mass of this. And that is going to be the mass defect. So Q is going to be equal to 236.053 minus 234.83, all in U. So 236.053 minus 234.83. So Q is going to be equal to 1.223 U. Now remember that 1 U is given as 1.223 times 1 U is given as 1.66 times 10 raised to minus 27 kg. So I'm looking for the mass of the amount of the energy released, the mass of the energy. Remember, according to Albert Einstein's relativity theory, that mass is equivalent to the energy. So that was determines the energy. So when I multiply that, I'm going to have 1.223 times 1.66. I'm sure 1.66, okay? So I'm having Q is equal to 2.030 times 10 raised to minus 27 kg. So this is the value of the mass in kg. All right, calculate the value of Q in joules. I have seen them in kg. I have to find it in joule. Okay, I have to find it in Joule. Finding it in Joule is going to be applying that same formula, E equal to change in mass. This is the mass defeat actually. So this is going to be E is equal to change in mass C squared. So E is going to be 2.030 times 10 raised to the power minus 27 times 3 times 10 raised to the power 8 all squared. So this is going to be 2.030 times 10 raised to the power minus 27 times 9 times 10 raised to the power 16. Okay, so this multiplied by 9, this times 9 is going to be 18.27 times 10 raised to the power minus 11 joules. Let's keep it that way because I can still rewrite this in a better way. So this is the value of the energy Q. State three differences between fusion and fission. In fusion is all about the combination of nuclei. Okay, let's define that. Is when we talk about fusion is the combination of the nuclei of light atoms to producing a heavier atom with the release of very massive energy, and the temperature involved in this case is very high to about 10,000 degrees Celsius. These are the two things about fusion. And the third one is that the field involved in this fusion is deuterium and tritium. Now, coming to the other fission is the breaking down or the splitting of the nucleus of a heavier atom by producing more atom with the release of heavy amount of energy. But the energy is not as much as that of the fusion. And again, the fission can also be used in power plant. Production of power plant is one of the advantages of the fission. Now, the last thing I want to say about fission is the field in using for the fission is uranium, is basically uranium. So these are the three differences between the fission, the fusion and the fission. Thank you for being part of this class, and I wish you luck in your physics exams. Your comment section is always there for interaction. Have a nice time.